Okay, let's see what we have here. The dream police, just like the math police, live inside of my head. Anyway, with that being said, let's have a little video here on trigonometric integrals. Okay, you might be wondering, hey, haven't I learned a little bit about trig integrals in a past life? Yes, you have, but as everything you kind of encounter in Cal 2, we start looking at more sophisticated things. So that's what makes integration, quite challenging. I say fun, but other people will probably disagree. Fun and challenging. It's kind of the more you know, the more you start learning, the more knowledge you have, and therefore it makes looking at problems in general challenging, as you know so many new ideas. Like, which one do I apply? Okay. With that being said, now this is these first two are integrals that you could run across in Cal 1. They're just basic substitution integrals. And so if you sine of cube, cosine of x, in fact, if you have sine and cosine multiplied together and one of the two is to the first power, it's just straight substitution. So this one, and you let u be the one that's not to the first power. So in this case, u would be sine of x. Real easy. So you're just integrating u cubed. You get 1/4 sine of x to the fourth plus c. And there you go. I just kind of write two different ways correctly to write. Maple does a little bit different, but this is the handwritten way. Because this is a little bit different, showing you that it's different than this, because this notation would imply that it's sine of x to the fourth. But both those notations represent sine being raised to the fourth. So same thing here, sine to the first power, so you have to let u be cosine. And no problem, the du will be a negative sine of x. You'll have to adjust for the negative. And you're just integrating negative u to the 3/5, no problem. But now we're starting to getting in stuff like this. Sine cube x, cos squared x. Sometimes in face-to-face classes, I'll ask this. A lot of times they think, well, let u be sine cube and that'll give you cos squared. Well, that's not true. The derivative of sine cubed is actually 3 sine squared times cosine. Think of it as being u to the third, which is 3u squared du. So that won't work. So let's look at these little techniques. I have these on my formula sheets, but it's not direct plug and chug. You need to kind of know how to use them. It's not like, oh, okay, well, I'll just plug this formula in. This just shows you how to get the integral started. This is not giving you the result of the integral. It's just telling you how to do the process. So it doesn't totally give everything away by having this. You still have to be able to integrate, but it does help you get started. All right, sine is odd and positive. You save one sine factor and convert the remaining factors to cosine, then expand and integrate. It almost sounds like a recipe, bake for 400 degrees for 20 minutes and let cool or whatever. But anyway, this will be our little recipe then, won't it? Okay. All right, so this is, what you see the examples. That's why this might not be that easy to follow anyway, just by looking at it. But then if we have cosine is odd and positive, we'll do a little thing here where we save one cosine for as your du and go from there. Now you might be thinking, what if they are both odd and positive? That would be an excellent question. Like if it was sine cubed times cosine cubed, that means you can use either one of these two formulas. I avoid that on an exam if it was a multiple choice exam, I would avoid that because I want to make sure it can only be done one way. But if I gave this kind of question on a handwritten exam, and technically I would have to accept the answer that's in terms of sines and the answer that's in terms of cosines. You know, if you that one example I did, if you watched my video on integration by parts, where I talked about the two different algebraic answers looking different, but their derivative would be the same. That would apply here too. Like if you had both of them odd and positive and got signs one way and cosines the other, as long as their derivatives match the original integral, which they would, that means they are technically both correct answers. So, and if we have even non-negative, it can be individual, like you could be integrating sine to the fourth or cosine to the fourth, or they could be multiplied together, sine squared, cosine fourth. You use these identities because you can't use the normal Pythagorean identity here to integrate, because if you take sine squared and go, oh, I'll just write that as 1 minus cosine squared, which you are going to be doing for this technique. That's different. That's totally different. But I mean, just to integrate sine squared by itself, and you want to write it as 1 minus cos squared, well, then the million-dollar question is, how do you integrate cos squared? So you're kind of stuck. So you have to use these two identities. So let's give it a whirl and see what happens. Sine cubed cos squared was the example I wrote down there. So according to that sine and positive, odd and positive, now when you're writing these out, you don't necessarily have to write the save for du there. That's just for illustration purposes. So I took away a sine from the sine cubed, put it with a dx, and left a sine squared there. Obviously, this part here better multiply out to be what you have in the original. And since sine's my du, that means I want cosine to be u. So I have to replace sine squared with 1 minus cos squared, because I want to be integrating cosine to get sine. So I replace sine squared with 1 minus cos squared, then I kind of distribute. That looks kind of weird distributing to the left, but that's okay. This looks kind of strange at first. Now you can split them in two integrals if you want to, but that's not necessary because they're going to be using the exact same du for both integrals, so you can leave it as one integral with separate terms. You don't have to rewrite this. In other words, because cosine squared times 1 is just cosine squared. Cosine squared times cosine squared is cosine fourth. Now, if you want to write two integrals with cosine squared sine of x minus cosine, another integral with cosine fourth sine of x, feel free to do that if you need to, but you do not need to because, like I said, they are using the same du here. Well, so what we've effectively done is we took this situation and now we have created two integrals that we can just use regular substitution on, like the ones I had on the first page there showing you that I called Cal 1 integrals. Because then you let u be cosine, du will be negative sine, so we're just off by a negative here for matching this in the blue. But that's okay, move the negative out here, so we have a negative to adjust for. So then your integral just becomes the negative of u squared minus u to the fourth, basic power rule, so I sort of distributed and did the power rule in the same step. So we have negative 1/3 u cubed, and antiderivative u4 will be 1/5 u to the fifth, but now plus 1/5 u to the fifth, and then substitute what u is, and then there's your answer. How about that? Pretty slick. Now, I did it in Maple, so I don't know why I reversed the order of the original problem. I don't know why I put cos squared first, sine cubed. I don't know. Okay, answer looks different, but strictly, yeah. Trig is sometimes trig integrals are difficult to show in Maple because with how trig identities relate to each other, the Pythagorean identities, you often get completely different looking answers than you would as a person would working it by hand. Working it by hand, you would match what I have. So this is equivalent, but then I took the derivative of it, and if you distributed all this out from around your 1/15, blah 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 blah, you would match that answer right there. But don't worry about that. So I can't get as excited about showing trig integrals in Maple because you get kind of weird answers. It doesn't accomplish as much. Now, one thing to keep in mind is that if you have higher powers here, other than this is true also for cosine, squared being 1 minus sine squared. If you have fourth power, you would have to write as sine squared squared, which becomes 1 minus cos squared squared, which then you be careful, don't, you got to make sure this is Cal 2. You should know how to square a binomial by now. You don't just square the first two terms, FOIL it out. You'll have 1 minus 2 cos squared plus cosine of the fourth. You have three terms. If it was sine 6, you'd have 1 minus cosine squared cubed. Now, let me mention that. With that being said, on these kind of problems, I never make a student do anything more than square a binomial, just because it's too tedious and messy. And so even though I wrote this last part down here for illustration, there is zero chance I would expect you to take 1 minus cosine squared and cube all that out. No chance. But I just wanted to show you that's the pattern of what would happen. Okay, so never ever will I make you do anything more than a square. So now we're going to do an example using the second one where cosine is odd and positive this time instead of sine odd and positive. Okay, looks like it might be scary with that square root of sine of t. We don't care about what the power of sine is. Cosine's odd and positive, so no problem. Just radical makes it 1/2 power. Bring it up to the top. So it's just sine to the negative 1/2. It's not going to make the problem any more difficult. It just means that when you do the u substitution, you'll have fractional exponents instead of integer exponents. But, whoop-de-doo, it's not that hard to do the power rule on, u to the 3/2 as it is u to the third, really. But all right, so I take away a cosine from here. Save it for my du. That leaves cosine fourth. I have sine the negative 1/2 t, so I have to convert this cosine to the fourth into sines, as I mentioned right here, in order to be able to do a u substitution. So cosine of fourth will be 1 minus sine squared squared. So you see I showed the FOIL here, obviously. FOIL it out. You'll get three terms, 1 minus 2 sine squared plus sine to the fourth. So you see, there's that step. So there's this step, so we'll skip that. Now I have these three terms right here that come from right here. Okay, now we have to, I showed the distributing going this way. I don't mean that to be confusing, but that's what's basically happening. Maybe I should have put this sine, the negative 1/2, in front of the parentheses, but that doesn't make any difference. It's still distributive property, just right to left instead of left to right. So I'm taking sine of negative 1/2 and I'm multiplying it by all three of those terms in the parentheses. All right, well, the first one's multiplied by 1, so it's obvious. But let's look at the next one. Sine the negative 1/2 times sine squared, add the exponents. 2 minus 1/2 is 3/2. Next one, sine the negative 1/2 times sine fourth. 4 minus 1/2 is 7/2. So there we go. So just like the last problem, you do not need to split this into three integrals if you do not want to, since they're all using the same du. Okay, looks like I guess to be helpful here, I just rewrote the power rule. I didn't write it earlier, but there it is. As long as n's not negative 1, of course that means it's natural log. But, there's your power rule. So there's, see, like I said a few minutes ago, well, now we have three terms because we squared that binomial. So we have three integrals instead of two. But they're all power rules. You just do the power rule. And, I'm not going to show that. That's simple enough. You'll come up with these three results. Obviously, you can shoot me an email if you had a question or something. But we do the power rule 3 times. And this one you don't have to adjust, unlike the other one we had a negative, because the derivative of sine is positive cosine. So we don't have to adjust. So we have these 3 terms, and then you put what u is in there. U is sine of t, so there it is. 2 sine 1/2 t to the 1/2, and then 4/5 minus 4/5 sine of t to the 5/2, plus 2/9 sine of t to the 9/2 plus c. Just for grins, I did it in maple. If you distribute all this business here, it'll match that answer right there. But you are not going to be required to factor that out and make it look like this answer here. So I do have, sometimes I'll have problems where it has, the answers are kind of factored, but not like this kind of problem. It'll be a little more straightforward. It wouldn't be quite this messy. All right. Well, okay, I'm going to kind of skip through this one a little bit. Cos cube, sine cube, like I mentioned this one earlier, you can choose either method. This one's not too bad. It's very similar to the first example. And this is just showing you what I was saying earlier. So if you choose this method, your answers are in terms of sine. Yeah, this one's really easy. And then you don't have to square a binomial or anything here. Now, of course, if you choose this method, you have the negative for your du you have to adjust for. That's the only difference. So you end up with sines one way, you end up with cosines the other. Oh, okay, I actually showed it here. That's good. I'd forgotten I'd done that when I said earlier in the video here. I forgot I did this. But look what I did. I took the derivative instead of using trig identities. It was much easier to show it by the derivative, like I was explained. I told you earlier in this video, and also referring to the the integration by parts video. But anyway, long story short, I had to do a symbolic simplify on both of these, but they both reduced sine cube, cos cube. So that means that just proves they were both correct answers. Like I said, I avoid that on a test. Now we'll take a quick peek at this one. Now, okay, they both apply, but I'm saying here though is it's easier if you break up the smaller power, and you'll see the next, and you'll see why in a minute. You know, I generally wouldn't put this kind of problem on a test, but I like to show this to you anyway. So I'm choosing the breaking away the sine here and converting to cosines. So I take away a sine, leaves a sine squared. So we make the sine squared be 1 minus cos squared. So that you distribute, you'll get cosine of 7, cosine of 7, cosine squared is cosine 9. And then your du is going to be a negative, so we have to adjust for the negative, but real easy. u7 minus u9. And with a negative, I did a little something different this time I normally do. You don't have to do this, obviously, but by sending the negative through there, I just reversed the two terms, but it's correct. But that's the same thing as saying negative u7 plus u9, just reversed. I don't know why I did that. And an easy power rule, so there you go. You have 1/10 cosine 10th minus 1/8 cosine x to the 8 plus c. The other way means you would take away a cosine from cosine of the 7th, leaves cosine of 6, but it would force you to take 1 minus sine squared and cube it. So there we go. I didn't even finish that one, so because there's no way I would ever ask that. But if you were a glutton for punishment and loved a good challenge, you could go for it. But then, like I said, unless you had some way to differentiate the software to see if it was equal or not, to know if you did it right, I would not worry about it. All right, it's cosine cubed of x over 3, so it's okay that you might think, hey, I've got I don't have two trig functions there. It's okay. It satisfies cosine being odd and positive. That's all that matters. So we take away a cosine, and then we convert cosine squared to 1 minus sine squared. You got to be careful here. The derivative of sine of x over the derivative of x over 3 is just 1/3. That's the same thing as 1/3 x. But then this time that becomes 3 when you flip it over to the other side. It becomes 3 du equals this. All right. So that's not too bad. So what I do, I took the 3. There's 3 du. So then so you have 1 minus u squared. So I distributed the 3. I could have left the 3 on the outside. That didn't matter, but I went ahead and distributed it. So now instead of later. So let's take the antiderivative of 3 would be 3u. Antiderivative of 3u squared would be u cubed. And there you have it. So it's 3 sine x over 3 minus sine cubed x over 3 plus c. All right. Here are the even powers I was showing you a little while ago that we haven't done yet, but now we're going to. Let's see what we can do with these. Now I'm just showing you here that that's why you have to use these identities, is because we can integrate cosine of 2x. Cosine of 2x, no problem. It would just be 1/2 sine of 2x. That's a good one to, like I said, I showed you this earlier in the integration by parts section. I showed this, it's in my notes. That's a good one to know, where you can immediately just go that cosine of 2x antiderivative is 1/2 sine of 2. Or I say, well, okay, let me clarify that. It's not always going to be 2x. Very important to realize when you're using this identity, and you'll see this in the first example. This isn't just 2x, it's double whatever your angle is here. So let's look at this. Sine squared 5x, you'll double that angle right here, makes it 10x. So let me clarify that. So you'll use this identity right here. So to integrate sine squared of 5x, we say, I just pull the 2, the 1/2 out, 1/2, and you have 1 minus cos of 10x. And then that's easy. Antiderivative of 1 would be x. Antiderivative of cos of 10x will be 1/10 sine of 10x. Now I have the 1/2 factored out here, but if you're choosing a multiple choice answer, you might need to distribute the 1/2 through the parentheses, but that's certainly not difficult. So that would be easy to take care of. Next one, we have sine squared 6x times sine squared cos squared 6x. So we use the identity for both of those. And so you have double the angle, so it's 1 minus cos of 12x over 2 times 1 plus cos of 12x over 2. Now I took the 2 2's out and put 1/4 out here, and if you actually FOIL that out, you're going to see you're going to actually lose a middle term, because that's the difference of two squares. It may not look like it when you first look, and then you stare at it. Oh yeah. In other words, x minus y times x plus y is always x squared minus y squared. But you didn't have to recognize that, because if you multiplied it out, you would see the cosine of 12x terms would cancel. So it's okay if you did not recognize that. All right. So we have the 1/4. But look what happens here. See, when you multiply, you have a cosine squared, so that means we have to use the identity again. Or actually, what I did, well, yeah, that's true. You have to use the identity, but I also noticed that 1 minus cos squared was just sine squared. But I could have done it by changing the cosine square, but it actually makes it easier to do it this way. But it would have worked. So sine squared of 12x, using our little identity there, would be 1 minus cos of 24x over 2. So there's the 2 from the right here from the denominator. I went ahead and brought it out with the 1/4 to give me a 1/8. And then very easy to say antiderivative of 1 is x. And then the antiderivative of cos of 24x would be 1/24 sine of 24x plus c. And once again, I have the 1/8 factored out, but you might need to distribute the 1/8 to match your answer, no problem. One extra easy step to do. Now here's cosine. Now we have cosine or sine to like a 4th power. And once again, I would not go higher than the 4th power, because I don't want you to have to do more than one FOIL there. Just now, when you have these two, you're not gonna have this situation of where you difference of two squares. You will get 3 terms there, whether it's sine to the 4th or cos to the 4th. So, all right. So you break cosine 4th 20t into cosine squared 20t times cosine squared of 20t. Use the same identity for both. Now I kind of just quickly pulled out the 2 2's out here and put the 1/4 to the outside. So yeah, it would have been 1 plus cos 40t over 2, but I've already took care of that. And another 1 plus cos 40t. Now you FOIL that out, you get 1 plus 2 cos 40t plus cos squared 40t dt. Now, because we still have a cos squared, we have to use the identity again. So cos squared is going to be 1 plus cos of 80t over 2. Now, after this, so there's no more identities that have to be used. You can kind of go about this different ways. I kind of like this way that I'm doing it here. Sometimes it's confusing for students when they first look at it, but it's easy. What I like to do is, you see this, when we had to use identity again, we created a new 2 here, that these other 2 terms did not have a 2 on bottom. So hey, I just created a common denominator inside here. So I just reached, since this is going to be over 2 right here, I made 1 be 2 over 2, and I made 2 be 4 over 2, just to get a common 2. Now when I do that, that common 1/2 can come outside to join the 1/4 and make 1/8. And then this 3 comes from where I drew the blue arrow right here. You're going to have now a 2, a loose 2 plus a loose 1 will make 3. Of course, that's now a 4, and then this did not change. Okay, so sometimes that throws people off. But if you look at it, now that I've explained it, hopefully that'll make it clear to see, oh, okay, that's what happened. But a lot of times, first thing, if I don't explain this in a face-to-face class, they look at this, and before I tell them, they want to know where that 3 comes from. So there it is. It's the 2 here plus the 1 there. Makes 3. Okay, now we're home free. Antiderivative of 3 respect to t would be 3t. Antiderivative of cos of 40t would be 1/40th sine of 40t, but we have a 4 right there. And then the antiderivative cos of 80t would be 1/80th sine of 80t plus c. Now, obviously, 4 over 40 can reduce to 1 over 10. Now, this one I did distribute. Okay, don't know why I did, but that's fine. That's good. So I reduced this fraction, and I distributed it at the same time. I came up with this answer. 3/8 t plus 1/40th sine of 1/80th sine of 40t plus 1/6 over 640 sine of 80t. Now, here are some rules for secant and tangent. I'm not going to worry too much about cosecant and cotangent. You could modify these rules to make it work for those, but I don't put those on an exam. But just for anyone else that happens to be watching this video, you can kind of sort of make it work the same way for cotangents and cosecants. Right. So secants even and positive, tangents odd and positive. If there's no secant, but you have a tangent that's even and positive. Now, secant. Now this was addressed in integration by parts notes. Secant cubes in the notes, and I have secant fifth to the end at the end of the notes. I had no intention of ever putting that on the exam, but that's but that goes. So actually, this just okay. So that's fine. Secant third, secant fifth, secant seventh. Ooh, that would really be bad. Secant pi is bad enough. Secant seventh would be a nightmare. But it's integration by parts. There's no rule from this section that applies to it. But we're going to use basically 1, 2, 3, and 5. We're just not going to use number 4. I'm not going to use it for anything. So I want to show examples of all these other ones. And if none of the first 4, you can reword that as saying the first 3. Convert to sines and cosines. And we're going to see some that do that. So if you look at the tangents and secants and go, hey, that doesn't fit, especially if it's a test problem, because it's going to be designed to have an answer. It's not like, the joke's on you, you can't integrate it. So you can say, oh, okay, then I'm going to convert this to sines and cosines. Alrighty. Secant fourth, cube root of tan x. Okay, that cube root of tan x is no big deal. It just means we're going to have fractional exponents to integrate. No problem. All right. So let's see. I'm kind of doing these in order, I believe. Secants, even and positive. We take away a secant squared now. With sine and cosine, we only took away the first power. Well, you take away a secant squared because secant squared is the derivative of tangent. So that's why it's a secant squared. And we're going to convert to tangents. That way, if u is tangent, you'll have secant squared as your du. How about that? So there's the save for du. Took a secant squared, left a secant squared because there's secant fourth. Rewrote this as to the 1/3 tangent to the 1/3. So we use the trig identity, and they have it. It's also on my trig sheet, but it's also right there here in the little recipe. Convert the the remaining sec squared to 1 plus tan squared. And just like I promised with the sines and cosines, I promised the same thing for this. The most you'll ever have to do here is square that parentheses, never more than a square. So I could have made this secant to the 6th if I wanted to. Never more than squaring. This one's not squaring though. All right, so we distribute the tan of the 1/3 through the parentheses. Just leave the sec squared sitting there. So tan of 1/3 times 1 is tan of 1/3. Tan of 1/3 times tan squared. Add the exponents. 2 plus 1/3 is 7/3. And we have, and that's, so there's your u and your du. So u to the 1/3 plus u to the 7/3. See, that's why you can keep them together as one integral. Just do the power rule. 3/4 u to the 4/3 plus u 10/3. And then replace u with tangent. So there you go. So there's our answer right there. And over here to the right, I'm just sort of illustrating what I've illustrated earlier, the proper way to write this. Obviously, if you're in an online class of mine, you're not going to be writing this, but but that's good to know for future stuff. If you do take a face-to-face, you should, if the tangent's being raised to the power, you should write it like that instead of this. Because if I'm me, or like most instructors look at this, they would think you mean the tangent of x to the 4/3. That does not look like the tangent's being raised to the power. Okie doke. Okay, so like I mentioned earlier, if something applies more than one rule, technically the rule will apply. I tend to avoid that on the test, so let's just pretend, for sake of illustrating the rules, that only the second rule applies. And that's for the tangent being odd and positive. But yeah, you could certainly argue the first rule. All right, this rule says that you take away a sec and a tan. I'm not going to scroll back up there, but you can see that in the description there. Take away a sec and a tan, like so. And then we're converting to secant because we take away a sec and a tan because the derivative of secant is secant times tangent. So you see it's important, I give you the inverse trig formulas, on my formula sheet, but you still need to know the basic, trig derivatives. So I take away a secant, take away a tangent, so it reduces both those powers by 1. So tan goes to 4, sec goes to 3. I convert to secant using the identity tan squared equals sec squared minus 1. So tan a 4th would be sec squared minus 1 squared, because the parentheses just represents tan squared only. So you have to square it to get to the 4th. So we do have to square a binomial here. There's our sec cubed. There's our du that it sits there. So once again, I'm doing my right to left distributing here. Sec cubed times sec 4th is sec 7. Sec cubed times sec squared sec 5th. Sec cubed times 1 is sec cubed. And don't distribute this. Leave that just sitting there as du. No, we don't want to distribute that, because you're letting u be sec to the 2x. Do not forget the chain rule here. Right? Because you're going to get an extra 2 here. So very important, because the derivative of 2x will be 2, which means we have to put a 1/2 on the outside to adjust for that. I didn't show the next line, but I didn't have any room, so I came over here. But so that's now 1/2. So now it's all just u to the 7th, 2u to the 5th, minus 2u to the 5th, plus u cubed. Power rule. Easy. Once you get this thing down to the final stretch there, it's not too bad. Antiderivative u7 will be u8 over 8. 2u5 will be 2u6 over 6. And then u cubed will be u4 over 4. And then we just substitute. No, see, I went ahead and distributed, like I said before. It's not, makes no difference mathematically whether that 1/2 is distributed or not, but I did, and then put u as secant of 2x right back in there. Okay, I just took the derivative of my answer just for fun. Obviously, you're not going to be responsible for doing any of this. simplified it, it looks different, but if you split up sines and cosines like I did here, that does turn into tan fifth, sec fourth, but not important. Not something you have to worry about, so I would not worry about that. Just worry about the integration. Here's another rule 2. So I guess I kind of, well, probably should have just not done the other problem and did this one instead, but okay, so I'm going to go a little faster through this one because this is really no different. I'll just kind of leave it slow on the page. Yeah, you save a sec and a tan, and you make tan fourth be sec squared minus 1 squared. And, all right, and then you'll distribute the sec fourth you have here through the parentheses. Yeah, that's really not much different than the last one. Sorry about that. Seems a bit redundant. I could have just could have deleted that one from the notes before and just did this one instead. But I've already carefully illustrated that second rule, so that's good. I don't think there's anything strange or weird about this one after we've seen that other one. All right, so I'm going to move on here. Okay, there's the maple stuff. Okay, now we're jumping to a new rule here. Rule 3. Tan sixth. This one's a little interesting because you kind of have to use a reduction property. You have to use a reduction property and keep reducing it downward here. So let's take a look at this. So you see, it wants us to pull away a tan squared and then change that tan squared to sec squared minus 1. It talks about expanding and repeating because this is tan sixth. We will have to repeat this. Probably even tan fourth we'd have to repeat it, but so it's just a little bit different. Not super bad, but it's a little bit different. So I took away a tan squared, and then I can, just like I did here, and convert the tan squared to sec squared minus 1, and I have a tan fourth. So this one, though, now this is a little bit different. Unlike all these other ones I've done, this one I do want to split into different integrals. This is we're not really sharing the same u du kind of thing here. Sort of are, but this one's better to split up. So I split this one up, tan fourth sec squared, and then I have minus just tan fourth times 1, which will be tan fourth. Now this first integral is no trouble whatsoever. It's just u substitution. Because remember, this is it looks like, oh, they're both higher powers, but remember that sec squared is the derivative of tangent. So we're good to go here. So this technically could be considered like a Cal 1 integral because it's basic substitution. So I left this here. And don't forget the chain rule. So the derivative of that tan of 3x will be 3 sec squared 3x, makes that 1/3. So we have a 1. So we just have 1/3 u to the 4th. So then we have 1/15 because you have a u. It makes it u to the 5 over 5. So 3 times 5 is 15. Tan of 3x to the 5th. And okay, so that's that part of it. So we leave that alone. Let's come back over here. Now tan fourth, we have to repeat the process up here again. That's what I mean by expand and repeat if needed. Yes, repeating is needed. So tan fourth breaks down into tan squared, which breaks down into tan squared times sec squared minus 1. So this one gives you tan squared sec squared. And once again, I'm using the same u and du, so it's 1/3 u squared. And then this last tan squared, you just use this identity again. Because sec squared has a natural antiderivative, it's tangent. So once you get it down to sec squared, then you're done. So you split them up again, and like I said, just this tan squared right here, just rewrite as sec squared minus 1. So we basically have this term carried all the way down. Now I have, so that's a u squared du, so I have 1/9 u cubed. This is just du, sec squared 3x dx. See, that's your d, well, the 3, we have to adjust for the 3. So it's 1/3 du right there. That's just, or you can just integrate it directly and call it tangent right here like that. You can skip this step if you want to. And that's just the antiderivative of 1 dx. So it's kind of weird that this answer is going to have an x in it. You would expect every term to have a trig function, but no, that's certainly possible that you can have a trig integral with an x term in there like that. So the antiderivative of sec squared 3x would be 1/3 tan of 3x, and this is 1/9 tan cubed negative 1/15 tan fifth, and then minus that little x at the end plus c. Well, Maple integrated this one in a much more pleasant form for us to look at. Now, the way I was talking about earlier, how you should write trig functions raised to power, Maple kind of contradicts me on that, which is fine. The way they do it, though, I know I don't like it, but I'll live with it. That's not 3x to the fifth. Their notation, that does mean that it's tan to the fifth. I know I don't like it. That is tan cubed. All right, this next one, we're bringing in rule 5. I didn't label it rule 5. Sorry about that, but well, I can do that right now, I guess. Because I want to go through and show you the other kind of run through the other ones and see why they don't fit. Now, what you have to be careful of, first of all, when you're looking at this, is you might think, hey, secant's odd and positive. No, it is not. When it's in that denominator, keep in mind that that is secant to the negative fifth power, technically, not positive 5. So, that's why it doesn't fit. So look up here. So where are these things? Yeah. Secant even and positive. Well, obviously that's not right. Tangent's not odd and positive. And so if there are no secant factors in tangent, even and positive, none of that fits. And I'm not using number 4, so there you go. It is convert to sines and cosines. All right. Now, all right, so we convert to sine and cosines. Bring this up here. So let's see what happens. Tan squared, of course, will be sine squared over cos squared. And secant fifth is 1 over cosine to the fifth. Get all that on the same page. And you just, like you do with any fractions, flip over and multiply. And then we end up with sine squared cos cubed. Okay, we looked at something like that earlier. So yeah, just because, that, you convert to sines and cosines, then you still might need to use a sine and cosine technique. So that's what we have to use, a sine and cosine technique. That's a real easy one. So we convert the, okay, start lifting these up a little bit. So now we're reverting to that technique. So, but it's possible to use, another technique after you've done that, sine and cosine. All right. This is real easy. Save a cosine, sine, convert to cos squared, 1 minus sine squared. Okay, this is easy. I think you can handle the rest of this. But the main thing is we illustrated the process of converting it to sines and cosines. That was the key. Okay, so let's look and see what's next. All right. Just trying to move something here. My mouse to select everything. Move it down just because I had some room. That's fine, no big deal. That's all right. So let's look at a new technique here. Integrating sine cosine products with different angles. These are all going to be raised to the first power here. What we're basically doing is integrating something like, you'll see, like this one, see sine of 5x, sine of 4x, sine of 2x times cos of 8x, that sort of thing. So the trig functions will all be to the first power. But you can't use a normal substitution technique because obviously, yeah, if you had sine of 5x times cosine of 4x, you could not use a normal du process here. These aren't too bad though. Now sometimes I'll see students make a mistake that on a handwritten test especially, I don't necessarily see that mistake on a multiple choice test because I'm not looking at the mistakes, but anyway. All right. Is those identities that I've given you or giving you that are right down here, sometimes people will think those are the answers to the problem, like, oh, that's the integral result. No, that's just the trig identity that is needed for you to get the solution. So I'll have people, like I said, they think the right side of this equation is the answer to the entire problem. Absolutely not. It's just the identity needed. Then you still have to integrate this right side is what I'm getting at. I mean, these aren't difficult really, but they'd be super simple if you didn't have to even integrate them. Okay, so sine of, and I wrote these two things over here in red just because keep those in mind. Not that you have to, well, if you're like trying to convert your answer to the right answer, because with the pluses and minuses and stuff like that. So let's be aware of that just in case. That sine, that's on the trig sheet that I give you also too. But to make sure you don't mess up on negatives and positives, just be real careful that technically sine of negative x could always be written as negative sine of x. So like if you had a result that you came up with and you got sine of negative 6x, the answer choice could be negative sine of positive 6x, and that would be correct. And cosine of a negative angle always equals cosine of a positive angle. So let's using these. So the 1/2's to the outside here. So you see it's just cosine of, and that's why it doesn't matter which one you choose as m and n, but it's probably easy just to stay in this order. It just makes it easier. So here I let m be 5, n be 4. So to integrate sine of 5x times sine of 4x, all you have to do is treat it as 5 minus 4 is 1. So you're just integrating cosine of x minus cosine of 5 plus 4, which is 9x. So you just integrate cosine of x, which will be sine of x. The antiderivative of cosine of 9x will be 1/9 sine of 9x. And then, of course, the 1/2 here on the outside from the formula, which you may need to distribute to match your final answer. But I just left it there. But so obviously, here's one with cos of 3x times cos of 7x. I let m equals 3, n equals 7. So I went ahead and copied the formula. So here it is. You gotta be real careful. These formulas are kind of close to each other. Like this is very similar to the last one, but you see, well, actually the first and the third are the ones that are similar. And this is the third one. You see the difference is the difference only negative and the positive right there. So be careful. So if m is 3 and is 7, like so you could reverse those if you wanted to make it easier, but I just did it just because I wanted to do it this way to show you. So 3 minus 7 is negative 4. 3 plus 7 is 10. So the antiderivative of cos of negative 4x, if you're just doing it, obviously if you realize that that's cos of positive 4x, you can go from there. But I went ahead and pretend like I didn't know that. So the antiderivative would be negative 1/4 sine of negative 4x. And then the antiderivative of cos of 10x would be 1/10 sine of 10x. So then instead of making the angle positive here, I went ahead and used this result in the very last step. So you can't pull a negative out of cosine, it just turns to positive, but you can out of sine pull the negative out with that negative, make it, and of course then I distributed here to get the 1/8, but this time I distributed. Sometimes I do, sometimes I don't. But anyway, then that becomes the positive angle. So either way, if you would have changed this to cosine of 4x, positive, you would have gotten positive 1/4 sine of 4x and then times 1/2, and you still would have gotten the same answer. But I'm just guessing an answer on a test is not going to have a choice. We'll probably not have it with a negative angle there, so I would expect to be able to convert it to positive. But that's not difficult, just using these. Oh, there's Maple answer. Maple certainly didn't leave it negative either. Oh, okay, well that's good news. I put this secant fifth on here just for grins, and no, I'm not going to go through that. I think there's an error in here somewhere I need to fix anyway, so I don't, that's totally, if you're just interested in the challenge, then knock yourself out. But yeah, this, I made a little blurb here. Not on the exams. That's usually enough for students to tune out right there. So with that being said, I kind of put the flag here, meaning that's, anytime I put the flag, meaning that's correct answer, but I guess I could put the flag in 2 places there, but yeah, that means that's right. So is this one's correct. So, all right, that's the end of this video. Trigonometric integrals. I forgot to change the, well, I don't know if it matters much now, but I was going to get rid of the section number for posterity's sake here, but oh well, that's all right. You've already seen it, but there it is, trigonometric integrals. All right, that's the end of this video.